dark hum of data centers. A single thought? Can AI be made perfectly repeatable? You ask the same question twice? You expect the same answer, but sometimes you don't get it. That small inconsistency is a real problem for science. Researchers dug into why deterministic settings still produce different outputs. At first, the blame fell on low-level math, floating point rounding and GPU quirks. The idea made sense. Tiny numerical differences add up. But tests told a different story. On a single GPU, repeating the same big matrix math gives the same result. So the math itself wasn't the main villain. The real culprit was higher up, the way servers process many requests. It's called batching. When you call an AI API, you're not alone. Many users send prompts at the same time. Servers group those requests into batches to run them efficiently. How the work is split and ordered can change the internal calculation order. That tiny change can shift which words the model picks. So the same prompt at different times can ride inside different batches. Different batch sizes, different scheduling, different result. From your laptop, it feels random. From the server's view, it's deterministic for a fixed batch, but that's not good enough for reproducible science. The fix required rethinking core operations inside the model. Researchers focused on three heavy hitters: normalization, matrix multiplication, and attention. These are the building blocks of transformer models. Normalization often splits work across cores for speed, but splitting changes the order of computation. The new approach: force a single, consistent computation pattern. Yes, it can be slower, but the output doesn't drift. Matrix multiplication libraries also change method depending on input size. To guarantee the same result, teams forced one consistent algorithm every time. That cost raw speed, but it bought exact repeatability. Attention was the trickiest piece. Models often treat cached tokens and new tokens differently to save time. That adaptive behavior made results depend on prior context and batch layout. So the researchers made attention behave uniformly. No special cases, no shortcuts. Once the changes were in place, the results were dramatic. Run the same prompt 1,000 times with no randomness, and you get the same answer every single time. The old system produced dozens of different outputs for the same prompt. The new system produced identical outputs. It did cost performance. A generation run that used to take half a minute might take nearly a minute now. But for research and training, repeatability matters more than raw speed. Why does this matter beyond neat science experiments? Training techniques like reinforcement learning rely on matching behavior between training and inference. If the model acts differently in production than during training, learning can break. Stability in inference leads to stability in training. Now, a quick leap from kernels to the laboratory. AI isn't just stabilizing code, it's starting to invent. Scientists have begun using generative systems to redesign experiments and instruments. Take precision instruments used to detect tiny signals in physics. One such detector looks for gravitational waves across kilometers of vacuum tubes. Designing those systems used decades of human intuition. Then AI was asked to reimagine components from scratch. What came back sometimes looked bizarre. Asymmetric layouts, weird mirror placements, at first glance, nonsense. Then engineers checked the math and the designs worked. In one case, AI suggested adding an extra optical loop that circulated light in a novel way. It used obscure noise reduction tricks researchers had not combined before. Analysis showed the tweak could measurably improve sensitivity. That's AI pointing out a non-obvious shortcut after decades of human effort. Across quantum optics and entanglement experiments, AI has proposed alternate setups that are simpler and more efficient. Some designs were built and validated in real labs and performed as predicted. That's more than automation, it's discovery. AI is also finding hidden structure in raw scientific data. Models trained on particle collision results rediscovered known symmetries. Other systems produce compact formulas that fit observations better than existing heuristics. They don't explain why the math works yet, but they do reveal new patterns to investigate. So, what's the big picture? On one side, researchers are fixing AI's plumbing so results are repeatable and trustworthy. On the other side, AI is starting to suggest truly novel experiments and designs. Determinism enables reproducible studies. Creativity opens doors to previously unseen possibilities. For creators and scientists alike, that means two things. First, rigorous, repeatable AI is essential for credible research. Second, when used responsibly, AI can accelerate discovery in profound ways. If you're a creator, practical advice: log your model versions, fix randomness settings, and note runtime environments. If you're a researcher, validate AI-suggested designs in the lab before trusting them. And everyone, remember that reproducibility is a cornerstone of science. This is not the end of the story. Some argue we should keep models stochastic and let them surprise us. Others say we must lock behavior down for the sake of science. Both paths matter, and both will shape the future of discovery. The hum fades. A single line remains: make AI reliable when you need it, and let it be wild when you want it to invent. Thanks for watching. Drop your thoughts below. Should AI be tamed or unleashed? Like, subscribe, and I'll see you in the next deep dive.